That's fine.
Mhm.
Oh, wait, I think it's this one. Yep. Yeah. You want to go? Use mirror. You could mirror it, but I think this might actually, yeah. Do you want to just mirror it? Do you want to call the thing first and so have this ditch thing open? Yeah, I guess it's top right. Turn on recording. Yeah. We can just talk. Is it recording on? Yeah. Right. You sure? Yeah. Okay. That's great. Oh, yeah. I didn't know.
All right, cool. Yeah, we're gonna go ahead and get started with today's lecture. So today's lecture is gonna be on vector quantization. And yeah, this is my first time lecturing, so my name is Derek. It's nice to meet you guys. And yeah, without further ado, we can get started. Yeah, so today's outline is pretty much gonna be a couple different things. We're gonna talk about the motivation behind vector quantization, followed by a couple different very famous models that use this concept, and we're gonna talk about how it applies it. So specifically, we're gonna talk about VQ VAEs, which kind of builds off of the VAEs we talked about last week, as well as VQ GANs, which builds off of VQ VAEs. And lastly, we're gonna talk about language prompting and how to connect NLP with these topics. So very famously, like for example, the DALL-E 1 model that came out of OpenAI a couple years ago, we're gonna discuss like at a pretty brief level, like how that kind of works. Cool. So what is vector quantization? If you haven't heard of this term before, it's essentially a classical digital signal processing technique, and its primary goal is to reduce the dimensionality of data. So if you've heard of PCA before, vector quantization kind of achieves a similar goal, but goes about it a little bit differently. So the key advantages of vector quantization can be broken down into four main parts. So first, it simplifies high dimensional data down to a lower dimensional space without losing too much of the underlying information and patterns. So as I said before, this goal sounds very similar to PCA, and the reason for that is because the motivations behind both vector quantization as well as PCA are very similar. We want to be able to reduce this high dimensionality data into a low dimension. Second, VQ provides a method for learning discrete latent variables. As we'll see later in this lecture, this idea is used in VQ VAEs as well as some other models as well. The reason we want to use discrete latent variables versus continuous variables have a couple of different reasons, and we'll go into this a little bit more further later. But essentially, it's because we want to use discrete variables for different situations. And it's much more easier to interpret this discrete variables as compared to continuous variables in a couple of different settings. Thirdly, VQ uses the construction of a codebook, which we'll go into a lot more detail in a bit. And lastly, VQ is used very often in generative models, as we'll see very soon. So that's the high-level overview of what VQ is. We're going to briefly go over what VAEs and GANs are. So starting with GANs, from a couple weeks ago, we've talked about both of these topics in previous lectures, but in case you've forgotten, we're going to briefly summarize them again. So GANs are essentially a neural network model that uses two networks within it. One that's a generator that generates data, and another has to guess or discriminate whether it looks real or fake. And based off of that, we have something called the GAN game, which is where these two neural networks are essentially competing against each other, and the only way for the generator to win is by generating realistic looking data. Secondly, we have VAEs. So these essentially combine autoencoders with latent variable models. So what that means is instead of outputting a single latent code word from our coder, we output a Gaussian distribution instead. So this is trained with a reconstruction loss and a regularization term in order to force the Gaussian distribution to be stable. And at the bottom, that's an image of what the VAE architecture looks like. Okay, cool. So building off of VAEs first, we're going to talk about how vector quantization can be used to essentially upgrade these models. So before we go into specifically how VQ is used, let's talk about the continuous lane representation. So recall that VAE uses a continuous lane representation, but VQ VAE essentially claims that using a discrete latent representation might be better. So in the original paper for VAEs, we essentially used a continuous vector to represent the latent space between the encoders and the decoders. And so the reason this was chosen is because at the time, this was just the simplest to use, and it was just a good way to represent the data numerically. There wasn't like too good of a reason basically for them to use a continuous space. So on the other hand, researchers explored using a discrete space because they thought that a discrete representation serves as a possible different space that would offer different advantages. So let's push on this a little bit further. Why might we prefer a discrete space over a continuous space? So a couple of different reasons include many objects in the real world favor a discrete representation. So one example of this is actually in code generation. So in code generation, we have, even though code generation might seem like this open-ended, very complex process, it can actually be broken down into a discrete representation. So for example, the basic building blocks such as keywords, operators, and punctuation are all discrete, right? There's only like so many limited different number of ways that you can actually represent these. So for example, like if-else function, those words can be discretized essentially into like 0, 1, and 2, for example, right? There's not like a continuous space. There's not like an infinite amount of different keywords that exist within like a language like Python, for example. Secondly, we can even encapsulate syntax structures such as for loops, conditionals, and other functional definitions to also be discretized. Yeah, and so because of that, discrete representations also simplify modeling. Each category corresponds to a unique value, whereas continuous latent spaces don't, right? Because there's an infinite amount of values you can have, and each value doesn't necessarily correspond to something like in the real world that we can interpret. And learning these continuous spaces also required normalizations and learning dependencies between different variables, which adds a lot of complexity, especially when researchers try to extend VAEs to other use cases. So those are a couple of the problems that VAE has with the continuous space. So that's like the current state, or that was the state before VQ VAEs were introduced. Yeah, so if that makes sense, VQ VAE essentially proposes using a discrete space. But how does it actually do this? It does this by extending the standard autoencoder structure by adding a discrete codebook component. So what is a codebook? A codebook essentially maps a continuous latent vector to a finite set of discrete latent vectors. This idea of a codebook is essentially VQ. Like this is what VQ does. So anytime anyone refers to anything as using vector quantization, it'll always involve this use of a codebook. So mathematically, this is essentially written as that equation you see at the bottom. While it might look kind of complicated, it's essentially just taking the L2 norm and just minimizing it to find like the closest one. So as an example, on the right there is an example of a learned codebook. So this is like the representation of like, for example, before we had like a continuous space of like this 2D graph of all these different points, right? And let's say that the dots are our code words within this continuous space. If the encoder outputs a vector, like let's say the red X, it would get mapped to the code word represented by the green dot, because that's the code word that it's closest to, basically. So yeah, that's essentially how a codebook takes a continuous space and is able to turn it into like a discrete space. Okay. So pushing on this a bit further, these are actual implementation details of how the codebook works. So again, the more, I guess, full definition of what a codebook is essentially a collection of embeddings that the encoder outputs can map to. So think of this as like a dictionary of latent space representations that's learned over time. So this codebook is learned at the same time as the encoder and decoder, which enables the model to improve its quantization strategy as the training continues. So the way the codebook is actually learned is by using clustering techniques similar to, I think, just the most basic clustering techniques. So for example, on the right, we have like a more like complete example of what the codebook looks like when it's being learned. So at the beginning, we have like a bunch of vectors in 2D space. That's like our continuous space. And there's no way to make this discrete, right? What happens then is we use a clustering algorithm and we're able to essentially calculate out or learn these code words for these centers. And so those red dots are like the centers. And this is learned over time. And this training is done like as the same time as the encoder and decoder is trained. And at the very end, all those code words are essentially put into this dictionary. And that eventual dictionary is what's referred to as the codebook. So when we go to essentially like, we have like some vector in this continuous space. If we just look in that dictionary, we can very quickly find the corresponding code word. Does that make sense? Okay, cool. And then lastly, also note that in regards to the codebook, the quality and size of the codebook will greatly impact the model's ability to capture and and generate complex data distributions. So the codebook also needs to be complex enough, basically, or simple enough for different use cases. Yeah, so that's how the codebook works. And looking a bit further, how does the codebook actually work within VAE? Essentially, during the forward pass, each point in the latent space is replaced by the nearest vector from the codebook, which again is found very quickly because it's essentially a dictionary within our memory. So yeah, and then on the backward pass, how does it actually train and update? During the backwards pass, the gradients are passed straight through the vector or nearest vector to the corresponding encoder output. And this is what actually allows our model to learn new weights. On that diagram on the right, essentially it's saying that we have our codebook or we have our encoder outputs get put into the codebook has a new output which corresponds to some discrete variable. And this discrete variable gets pushed into the decoder. And then on the backwards pass, it essentially does this backwards. And that's how we can update our weights. Next, some of the more fine details of our architecture. Within the forward pass, our encoder actually outputs a series of vectors and not just one. Recall that in the original VAE, our encoder only outputs a single vector. So the reason that doesn't really work within VQ VAE is because if we only outputted a single vector, there's only like so many vectors it could output, right? Because it's put into a discrete space. And because there's only so few different, there's only so many different vectors that could be put into the decoder. What that means is that the decoder has a much harder time actually learning from these because there's just not that many things that can go into it. So what they do instead to make up for this is essentially using a series of vectors. So when you have multiple vectors, the encoder outputs a series of discrete vectors. And so by using this series of vectors, the decoder is able to learn more representations. More specifically, it increases exponentially in the number of possible decoder outputs. So yeah, so like for example, one image can output like a 32 by 32 grid of vectors, and our codebook has 512 vectors. Each of these vectors within the grid map maps to one of the codebook codes. And then our decoder input has 512 to the 32 by 32, which is a very large number of possible choices. So that's in contrast to if the image only outputted a 32 by 1 vector. Does that make sense? So in the very bottom bullet, in the original VAE setup, it would have only had 512 to the 32th power of output choices, which is significantly less than 512 to the 32 by 32. So that's the reason we need to essentially use a series of vectors. Yeah, And so on the right, that's like what the full VQVE architecture looks like. And yeah. So as for more fine details on the loss function, you might be wondering, how does the VQVE model actually update and learn? So the way it does this is by using, the paper introduces these three different loss terms, and together that's like the overall loss function of the entire model. So first they have the reconstruction loss. So this is essentially the what optimizes the encoder and decoder. So it's the first term in the bottom, the log of P of X. So there they use a log probability, and that's what essentially gives the gradients back to update the encoder and decoder weights. Second is the codebook loss. So embeddings themselves don't actually receive gradients from the reconstruction loss, the first term. So we need some other term in order so the codebook can update and reduce its loss. So what that means is we need essentially within our codebook, we want to find like, we want to minimize like the distance, right? So for example, if we look at an example of the codebook, one of the things I mentioned earlier was like using like a clustering algorithm to learn it. So what I'm talking about now, the codebook loss, is essentially like the clustering algorithm that finds like what an optimal low loss codebook looks like. So in order to do that, we use like an L2 loss, or more commonly referred to as like the Euclidean distance between points. So we want to reduce like the Euclidean distance between the codes or the red dots with all of the other vectors around it. So when we go to minimize that term, that's how we eventually learn like these red dots, if that makes sense. Okay. And then finally, the last term is something we call the commitment loss. So in the current setup, the volume of the embedding space is dimensionless. And so the discrete dimension space could grow to a dimension of arbitrary like amounts. So because of that, we need to be able to regularize it and make sure that this discrete space is still in like a low enough dimension where it's still less than the original high dimensional data. And so that third term on the right is what's used to essentially regulate that. Okay. Does that make sense so far? Any questions? Okay, yeah.
So we just have one loss function that does all three of these things every time.
Yeah. So this is the loss function for the entire model. And so they combine like all parts of it into this one loss function altogether.
Could you please explain to me again why the encoder, why the decoder has problems with the.
Yeah. So are you talking about like this slide?
Yeah, please.
Yeah. So essentially what I was saying earlier was that in the original, in a vanilla autoencoder, what happens is the encoder outputs like a single vector, right? And this vector gets passed into a decoder and it constructs like some, image or whatever, right? So yeah, I'll just use the example of images as the input and output for now. So that's how it works in the original one. It has a single vector. But in the original autoencoder, this latent space is a continuous space. So this vector could be like anything, essentially, right? So if it was even like 2D, we could have like 1, 1, negative 1, 1, negative 1.1, etc. And it could just go on like, there's so many different types of things that could enter the decoder, right? But what happens when we turn this continuous latent space into a discrete latent space, what happens is that there's only like so many limited number of discrete vectors that could be like used as the decoder input, right? So because there's very little diversity of data, the decoder is not able to learn like meaningful weights. Does that make sense?
Yes.
Yeah. So the way they like get over this is by using a series of vectors. So instead of just taking one vector, it outputs like 32 vectors, for example.
So it bunches them up and releases them at point that like when it has a bunch at a time.
Yeah. So it like concatenates them all together and it just gives this to the decoder. Yeah. So yeah, and the bottom example kind of illustrates that point. Like the decoder now has 512 to the 32 by 32 instead of 512 to the 32, right? So that's like a huge magnitude greater. And so that helps the decoder learn weights more like in a much more meaningful way. Yeah. So yeah, it's like a clever trick that the VQV paper does in order to like get over that hump of like decoders not learning anything. Okay, cool. Okay, yeah, so that's been the overall architecture of VQ-VAE and like the implementation of it. Now we're going to talk about some of the problems that it fixes that VAE could not fix. So the first problem, and a problem that's mentioned a bunch of times in the VQ-VAE paper, is this problem called posterior collapse. So this is a known problem for VAEs, and we're not able to use complex decoders. And so I'll talk about this a little bit more. But first, what exactly is posterior collapse? Posterior collapse refers to more accurately, a posterior is not collapsed if we can sample a latent variable z from the Gaussian distribution on the right, where both the mu and the sigma are stable functions of input x. When I say stable function, I mean that noise does not affect mu and sigma great enough when they're equations of x. So on the other hand, posterior collapse occurs when the signal from x is too weak / noisy. So if like we have like some image x and it's like a very noisy, weak image, what happens is that the latent continuous space that we learn that has like normal of mu comma sigma, this mu and sigma essentially mean nothing. Like these are just random constants. That's what happens when, that's what's referred to as posterior collapse. And so the issue with that is when this continuous space we have, this normal distribution of mean mu and standard deviation sigma, when this mu and sigma are essentially constant variables that don't mean anything, what happens is that the decoder will start outputting, the decoder outputs will have nothing to do with the decoder inputs. So like we want our latent variables that get passed into the decoder to be very closely correlated with the output images, right? But in posterior collapse, that doesn't happen. And the latent variables that get passed into the decoder are independent from the outputs. So that's like essentially like the premise of the problem. And so how exactly does VQ, or actually, yeah. So first in VAEs, what this looks like is essentially, I pass in a bunch of images to my model and the encoder encodes it, does whatever, but the decoder gives it like something completely not related to the input. That's like what happens in posterior collapse. And that happens because of the decoder, not the encoder. So that's like the premise of the problem that VAE was not able to solve. Does that make sense? So how does VQ-VAE actually fix this? So it fixes this through a couple of different methods. So first, we talked a bunch about this discrete latent space, right? Discrete latent spaces inherently avoids this posterior collapse problem because the model cannot ignore this latent space as easily because there's only so many different outputs it could have. Secondly, the decoder is unable to construct data without referring to these discrete codes, so it can't just ignore it. Secondly, the commitment loss that we introduced a couple of slides ago forces the encoder to produce a latent representation consistent with the entries of the codebook. So if you imagine like we have our codebook in like this 2D plane, what happens because of the commitment loss is vectors that are in this plane can't just be like super far off like this where most of the points are. So let's say like most of the points are like within like a very close distance. Because of commitment loss, we're not going to have vectors just like 100, like just a bunch far off, essentially, is what I'm saying. And because of that, they'll correspond more closely to the codebook, and we'll get like, let's see, we'll get better outputs essentially. Yeah, and that also discourages the model from ignoring latent variables. And so lastly, in the VQ-VAE paper, what happens is that they used something called a pixel CNN decoder. And so this decoder is a very complex decoder that uses something called autoregressive. It's referred to as an autoregressive decoder. And essentially it breaks VAE due to posterior collapse, but VQ-VAE works with it. And so, yeah, just to sum everything up, VAE suffers from this problem because when decoders are too complex, the outputs of the decoders will have nothing to do with the inputs of the decoder. But in VQ-VAE, they're able to solve for this by using, number one, discrete latent spaces and commitment loss. And so they're able to use any decoder they want, even if it's like a very complex, very like deep layered decoder. Does that make sense? Okay. Yeah, so this is like the largest problem that VQ-VAE solved within VAEs, as well as other improvements such as just the general like accuracy of the model. So yeah. Okay. Cool. All right, next, we're gonna transition from VQ-VAE1 to the second iteration of this model. So does anyone have any questions about like anything we've talked about so far? This would be a pretty good time. Okay, cool. So what is VQ-VAE2? Essentially, it's just a couple of architectural changes that allow VAE1 or VQ-VAE to learn more better representations. So the primary change that they introduced was introducing this idea of hierarchy. So specifically, they introduced a hierarchical latent space that captures information at multiple levels, not just one latent space. So this can best be represented by this image below. Here we see that this is a two-layered VQ-VAE, where we learn two different size latent spaces. So as you can see, the grid with, the square with like a bunch of grids and a bunch of like lines, that's like the latent space. So in the original VQ-VAE, we would have only had this bottom layer of the two blue squares, followed by the third blue square with like a bunch of grids. But VQ-VAE2 essentially says that we can have multiple layers. So they add another encoder layer on top of this first layer. And then we learn another latent space, which is the smaller like 4x4 grid of dots on top. And then that space, as well as the original large latent space, is what's used to encode the image. And then when we want to go reconstruct images, we again use both of these images or both of these latent spaces and pass it through the decoder, and we're able to learn an image with more fine-tuned details, like more fine details. Does this overall like idea make sense of like why they would use multiple latent spaces? Actually, yeah, we'll talk a bit more about why this works. Like, does this general idea make sense? Okay. All right. So like, why does this actually work? Essentially, the model is able to represent finer details by capturing like local and global aspects of the data. So actually, yeah. So specifically, in this bottom picture, we can see that like that first latent space, that first like the bottom grid, that is what captures like more global, like data on like a more global scale. But that smaller latent space above captures data on like a more local scale. So think like within a CNN, the power of CNNs is that you're able to capture like a lot of like locality, right? Like spatially aware data. This kind of tries to replicate that idea by allowing like some latent spaces to be like more local than others. Yeah, we have, and this is not only restricted to 2 layers, you could have like as many layers as you want, but yeah, the more layers you have, essentially, the more like local your data can be tuned, because you have latent spaces that represent specific amounts of like locality, if that makes sense. Okay. So yeah, one essentially result of this image is that on the bottom, you can see that if we only use one layer on the very left, I don't know if you can tell, but it's a pretty blurry image. And the more layers you use, the better it gets, basically. So like using 2 layers in this second to left image is like significantly better. And then 3 layers is like a little bit better than that one. So yeah, in that image that uses H top and H middle, we're able to capture a lot of the more like fine details of the person's face, for example. Like yeah, and so it's much closer to the original image. Yeah, and something else VQ-VAE2 does is that they use autoregressive decoders like Pixel CNN, which I mentioned a little bit before. But yeah, VQ-VAE1 uses a bunch of different decoders to test all their stuff. But this second version essentially only uses autoregressive decoders, which we'll talk a bit more toward the end. But yeah. Okay, cool. Any questions on VQ, VAE 1 or 2? We're gonna move on to a different section. So. Okay, cool. All right, so VQ GANs. So this paper essentially built off of VQ VAEs. I think one misconception is that like VQ or VAEs become VQ VAEs and GANs become VQ GANs, but that's actually not the case. So it goes from, the tree kind of looks like VAE to VQ VAE to VQ GANs. So this is kind of like a descendant of VQ VAE. So yeah, they combine VQ VAEs with the discriminator network from GANs, as well as introducing transformers in order to learn long-range interactions. So one key difference is that VQ VAEs use the decoder to reconstruct the images, but here we use both the decoder and the transformer to construct images. So that's the biggest difference, as well as the discriminator. So yeah, they introduce two basically, they combine it with discriminators as well as transformers to essentially get this new model. So yeah, so how do we train the VQ VAE plus the GAN? Actually, sorry. First, yeah, I should mention that this model is trained in 2 stages. First, it's the VQ VAE plus the GAN, specifically the discriminator. And the second part is that we train the transformer. So this is like a multi-stage training process. So starting with the first process, the first stage, how do we train the VQ VAE plus the GAN? Essentially, everything is the same, but we introduce a discriminator function. So if you see in the image on the right, this is like the difference from going from VQ VAE to VQ GAN. The main difference we're talking about right now is adding the discriminator on top of the reconstruction of the image that comes out of the decoder. So like more on the right side, you'll see like the discriminator model. So how do we train this VQ VAE plus discriminator is essentially what we're talking about right now. So the main difference is in the loss function. They changed 2 main things. So first, rather than using reconstruction loss, which is what's used to tune the encoder plus decoder, they use something called perceptual loss, which is what's used to train the encoder and decoder. So perceptual loss is essentially, instead of like a pixel per pixel basis of like the difference of 2 images, what they use is like human perception of it. That's like the high level idea of perceptual loss. Like if a human can look at 2 images and say, you know, using their perception, how different are these 2 images? That's like the intuition behind what this loss is. And so we want to maintain good perceptual quality, and we don't really care about like a per pixel basis like the other paper did. So what it is essentially mean squared error on 2 encoded images. So if you remember in the original one, VQ VAE, we used a log probability loss, but now it's a mean squared error loss on 2 encoded images. So as a more concrete example, like let's say we have 2 images that are passed through a CNN, so encoded, and the nth layer of their features are used as loss. So specifically, the first term of that L of VQ is our perceptual loss, the L2 norm of x minus x hat. That's our new loss. So the second part is the adversarial loss. So how do we train the discriminator? So this is what they use, this equation at the bottom. So d of x here refers to the probability discriminator d that says that a real image is actually real. And so, yeah, you essentially take the log of both the discriminator as well as 1 minus discriminator. I think this is referred to as like just another log probability loss as well. And yeah, so putting it all together, you essentially add up both of these and we use that to train this first stage. Yeah, any questions on this part? Okay. Yeah, so now that we've used this loss function to train the VQ VAE as well as the GAN, we want to train the transformer. So again, the purpose of this transformer is that we want to use it to output images. So how can we do that? We freeze the encoder and the decoder and we start training this transformer. So the codebook gives us a discrete sequence S, and we train the transformer on this discrete sequence S. So in the original image here, you can see that the transformer is connected to the codebook. You can see like a back and forth arrow there. And that's like what that means. The inputs to the transformer are the output sequence from the codebook. So the task here is essentially sequence prediction. If we have our encoded output from this codebook, we want to use it as our target sequence on the transformer. So specifically, at the time, they used GPT-2 and they used cross-entropy to predict the next token. So one example of this, a concrete example of sequence prediction is essentially, let's take a look at our codebook here, CFQ. So the input sequence is 1, 42, 3, 3, etc., all the way to 22. And so we're asking the transformer, hey, predict the next token for me. I'll tell you if you're right or not. And so the next predicted token should be 57, because we essentially take the codebook and we find it. Does that make sense? Yeah, and so that's like the process of training the transformer at a high level, essentially what we're trying to do. Okay. So mathematically, this is like a more like mathematical way to put it. We have this sequence S from the codebook. Given these indices S less than I, the transformer wants to predict the posterior P of S of I given all these indices less than I. This allows us to compute the likelihood of our full representation, which is given by the P of S. So that P of S can be used in the loss of the transformer in order to minimize the transformer loss. And so this is what's used to train the transformer, basically. So that's like the second stage of our training. So one final thing about the transformer is that it actually struggles with high resolution images. The reason it struggles is because in the current setup, the latent space is, for example, the latent space dimensions are reduced to like 16 by 16, for example. So let's say that we have like an image, and this works fine for images that are pretty small. It's like 128 by 28. We can compress it to 16 by 16, like pretty easily, right? Not much information is lost. But if we give it like a 4K image and we want to compress it all the way to 16 to 16, there's gonna be some problems, basically, is like the premise of like why there's a problem in the current setup. In an ideal world, they would have just increased the latent space dimension to match like a 4K image, but there were like computational restraints. So they had to use this trick, basically. So the trick is that the transformer uses a sliding window in order to, when it does its sequence prediction. So in like a really large image like this, like a 4K image is not actually compressed all the way to 16 by 16. It's compressed to something larger. And then the transformer is applied on top of that, both a sliding window. So like, for example, like, let's say like, instead of compressing it to like, ideally we'd want to compress it to 3 by 3 in this example, like, cause like the transformer's window is a 3 by 3, but let's say that we could only, compress it to 5 by 5. So in that case, what would we do? They use this idea of a sliding window for the transformer in order so that when the transformer is generating like each patch of the new image, it only sees like that portion of the image. So typically a transformer would see the entire image and generate the entire image at once. But now we're saying, let the transformer see a tiny patch of the image and generate that patch. So this transformer goes window by window to generate the patches of the output image. Does that make sense? Yeah, so we essentially want the transformer window to be smaller. And because of that, we use this idea of patches and windows. And so by the end of all of this, after training the transformer, image generation can be formulated as autoregressive next index prediction. So what does that mean? Given that the transformer starts with like a single patch, what happens is that I can feed this patch back through the decoder and get like the next, or back through the transformer and get the next and predict the next sequence. So if I start with only one patch, I can feed this patch back into the transformer and get the next patch, and I can keep repeating this process to generate the entire image. That's what autoregressive means, taking the output, inputting it back into the model, and then getting like this sequence, basically. And so that's like why transformers are so powerful. They're able to learn these like long-term representations and like meanings over long periods of time. So that's how the transformer works. So lastly, are there any questions overall on how VQ GANs work? After this, yeah, we're going to transition into language condition generation. So, yeah. Okay, cool. So moving on, how can we further improve upon VQ GANs and incorporate NLP and natural language processing into it? So specifically, we extend the capabilities of both VQ VAEs as well as VQ GANs by integrating NLP. We combine like the visual synthesis portion of these models with the semantic understanding of language models in order to generate pictures from text. So I'm sure everyone's seen like at least like a demo of how DALL-E works. You can tell it to generate any image, like similar to like, yeah. So a Midjourney is like another very famous example of like language condition generation. But specifically, we're going to talk about like the first two big players in this space, which is VQ GAN plus Clip and DALL-E 1. So VQ GAN plus Clip is like one model together. So how does VQ GAN plus Clip work? Recall that Clip is essentially a model that can take in images and predict like its text. It can like guess what this image is, like what's in this image. So with that idea, VQ GAN Clip refers to two separate models that work together to generate realistic looking images. So specifically, VQ GAN generates the images and Clip serves as a guide or a judge to essentially align the image to the text prompt that the user gave. So specifically, through repeated iterations, VQ GAN will improve the images based off of what Clip says. So here's like a cartoon kind of showing like this process. VQ GAN, oh shit, it's cut off at the top, but it says like starry night. Yeah, city during a rainy night. VQ GAN generates this image of like noise, right? You can't really tell anything. And so Clip says that, oh, this image is not very good. So VQ GAN iteratively improves upon it. And then Clip will eventually say like, oh, this is a good image, give it to the user. And so specifically, I think one common misconception is that VQ GAN and Clips are two models separate, and they're used together to generate images from text, basically. So yeah, this is the first approach, and one of the first papers that kind of came out in this space. Another one I'm sure many people are familiar with is DALL-E. So rather than using two separate models, DALL-E is one single transformer-based architecture model. And essentially, it's a 12 billion parameter version of GPT-3. But specifically, what they did was they were trained on text-image pairs in order to learn how to generate images from text. So in a couple ways, it's very similar to VQ GAN Clip and takes a couple ideas from it as well. So similar to Clip, DALL-E is an example of multimodality that bridges text and image. Similar to VQ GAN, DALL-E is also modeled autoregressively, which, as I mentioned before, we use the output, use it again as an input, and we can generate like a sequence. So here's like just an example of how DALL-E 1 works. If you tell it to generate like an illustration of like a baby radish, it'll do it. So yeah. So in conclusion, how do all of these concepts kind of tie together? This is a knowledge tree, or like a tree of essentially how everything is built up together. And essentially it kind of starts with, yeah, I'll start with like the parts that we've talked about in class more. So yeah, from neural networks, we developed autoencoders as well as CNNs. Then both of those were used together to create VAEs. VAEs and VQs were put together to create VQ VAE. And then VQ VAE takes GANs and transformers and creates VQ GAN. And then we take VQ GAN, combine it with Clip, and we get VQ GAN plus Clip. So this actually is a pretty cool representation of like everything we've like learned in this class and just in other ML classes and how they've all kind of come together and where we are now. Yeah. So yeah, that's kind of like the end of lecture. If there's no other questions, this is the attendance link. Yeah. Yeah. Yeah, if anyone has any questions, yeah, feel free to like just ask. All right, thank you all. Oh, yeah. Yeah. Oh, on the homework?
Yeah.
Oh, yeah. Yeah, sure, yeah.
Um. Just one quick one.